So I can start. So hello everybody. First I thank Alejandro for inviting me to give a talk at this really exciting event. The previous talk was exciting for me very much. So and there were also many things that maybe I will use or comment on during my talk because I will also talk a bit about NMC. But we are using quite different approach here, maybe here is just sketch what we are doing. We are using impedance on different kinds of electrodes, also on flat electrodes, on porous electrodes, and the porous electrode is nothing else but what was shown before by Abos. So we have something like this. Electrons, ions, electrolyte between particles, and so on. But we try to be more general. These active particles don't have to be in particles like NMC. They could be whatever. Also, inert particles on the surface of which something happens. So you have reactions like maybe in fuel cells, supercapacitors, or maybe in some batteries like sulfur batteries, and so on and so on. So it's we treat porous electrodes in a really general way. The main part of this is just that we have different transport paths of different lengths for both for ions and electrons, and this gives us the general framework of for what we understand as a porous electrode, pretty much similar as what the Newman model says. So yeah, okay. So before I continue, I want to present maybe the levels of modeling actually that exist in impedance spectroscopy community, and there are various levels, and the most used one is arbitrary equivalent circuits, where you just try to find an equivalent circuit that fits your data, your experimental data. This is okay, you can do that, but the problem is usually that you don't know the physical meaning of individual elements, or at least you are not sure about them. And then we have physics-based models where of course, we can make analytical solutions where possible of governing equations like Poisson-Nernst, Planck, as mentioned before, or Newman, as also mentioned before. Then you have these numerical solutions, which was already shown before. And then it is also possible to use another approach for physics-based models, and it is called transmission line modeling. Transmission line modeling is actually also can be used under first point, so like an arbitrary equivalent, or you can actually derive elements directly from the governing equations and then use them to cover processes locally and generally in your porous electrode that you have. So maybe this transmission line modeling out of governing equations is not that much familiar in the community, although there are many papers on that actually, not maybe so much in batteries, but elsewhere. So maybe I will talk about this approach later on. So I will explain very briefly what this is. But first, let me try to compare different levels of modeling, so just that we know what there exists there. So let us have a very simple model, a very simple case, active metal in electrolyte, and then you have transport and reaction at the metal. Now, if you measure, you will get something like this probably. So this is the measurement are the circles, the black circles. And then you can there is also, usually there is noise, especially at lower frequencies, and you have to be aware of this noise. You have to find in your measurement the noise. If there is noise, you can exclude it out of your analysis. And then arbitrary equivalent circuit level is something like this. So you have some resistors, some CPE elements, if you wish, and then you can or capacitors, and then you can fit this. Then the other approach, the analytical solution, is the typical example of this is the Rendel's circuit, very well known. Rendel's circuit is created so that you use governing equations, and then you solve them, and then you look at the solution, and you recognize elements, these kind of elements in your solution, and you just then plot your equivalent circuit. So this equivalent circuit is constructed based on the analytical solution. And then the physics-based transmission line approach is something like this. So you have governing equations, you transform them into elements in certain way, and then you use these elements to describe locally impedance everywhere in your system. And that's what we are doing mostly. So transmission line approach, and I will talk about this, show you some benefits, some deficiencies of this approach, but we also use some analytical solutions wherever possible. So, and we compare both approaches also quite frequently, if possible. So, transmission line approach based on PNP framework physics. So, if you have governing equations like those on the left, then you can rewrite them in a way that you have a correlation between current. So this is something that you want to have, and then the parameters that correlate these two quantities are either resistors or capacitors. So and then you can, of course, define resistors and capacitors, and typically wherever there is transport, and in porous electrode there is a lot of transport. Typically, you have two kinds of elements. One is resistors, migration resistors, so to say, and the other is chemical capacitors. And the coupling between them will also tell you something about diffusion. Usually, you also have electrostatic capacitors. Usually, this is neglected, but not always. For example, if you have a solid electrolyte interface, you might want to use these as well. So, but today we are not going to use this, but it's possible to do that, and it works very well. It has been shown in the literature many times. Now, if we go to this porous electrode, like I sketched it before, unfortunately, I don't have a very nice tomography. This would be even much better, but maybe others can send me data later on, and I can upgrade this kind of presentation sometime. So if we have this kind of schematics, then we can how do we make this kind of transmission line? So first we identify a sort of unit element, modeling unit element. Let's say that we have carbon black, which is pathways for electrons. Then we have electrolyte plane below the active particles, which is soaked with ions and conductive through ions in liquid phase. And then we have these active particles. And this is a sort of unit out of which you create then the whole electrode. And if you put this into sort of three-dimensional perspective, like here on top, so we have the same planes, electronically conductive on top, ionically conductive on bottom, and in the middle, where ions and electrons meet, we have actually insertion and then movement of charge inside these solid particles. And all of these can be then represented quite accurately, or really, I mean, as accurately as possible based on Newman or PNP model. With unit, actually this is only unit equivalent circuit or unit transmission line circuit here, and it describes all possible events, so to say, when this charge is moving here, inserting, these charges moving here, inserting, traveling together inside the particle, and so on. So this is directly transcribed from the equations and written like this. This might look quite complicated. It is a bit complicated, but in fact, you can deal with this probably very much easily than in the previous case than I was talking about. So here we have all these elements are certain capacitors, resistors, and so on, some elements which come out of equations. And here, for example, one element is mobility resistance, chemical capacitance, mobility resistance for lithium ion, for electrolyte in pore, chemical capacitance, electrolyte in pore, and so on. So you have clear physical description of all of these elements here, and each element, of course, has its own equation behind. So you can do the physics-based calculation at any time you wish. Of course, then in real electrode, you would use, I don't know, let's say 1,000 elements for each part. So you have slices and 1,000 slices for each process, and then you will get a very high accuracy of your output. So usually these transmission lines are shown in 2 dimensions. So now you can transform this 3-dimensional network into 2-dimensional, but usually you have to make some simplifications. For example, for NMC, that I'm going to show you further on, you can use this kind of simplification shown here. For example, here you don't see these NMC elements separately, which are here and here. So each particle has its own line of elements, so to say, and each of these lines transforms actually into one simple element called Warburg impedance, and in solid material. And Warburg impedance in solid material is analytically can be analytically expressed. So it's Warburg. So this works in some cases quite well, not in all. So you have to be careful when you do this kind of simplifications. But in our case, this is possible. So I will be using this simplified planar version most of my talk. So now, once you have cathode, which we were treating now, you add anode if you wish, and you add something in between, or you can also have cathode like Abos was having, and so you are free to choose from. Now you will say, okay, here let's say that this is NMC, the 3-dimensional picture that I showed you before. What is this then? What could be this? Let's say this is lithium. Now, if you compare these and this side, you will see it's completely symmetrical. And you will say, okay, isn't this part here intended for porous electrode? And if this is lithium porous? And the answer is yes. Although we usually say, okay, lithium is flat electrode, I will show you clearly with pictures and everything later on that lithium, especially cyclical lithium, is porous and can be described effectively with the same general scheme as the cathode. That's a sort of beauty of this symmetry here. Even if you have anode cathode, you can have this kind of symmetrical case, and then there is electrolyte in between. Now, very generally, I will go very briefly through this. So what do we see in this transmission line? We see transport of ions, which is described by this lower line of elements here. And this transport contains both modes, migration and also diffusion. So you have migration and diffusion from one electrode to the other electrode of all mobile species. Then on the top, you have electronic properties, as I said before, and you see movement of electrons in the cathode and in anode. Before, there was a question, do you see contact resistance? Yes, here we have contact resistance, this ZA. The first element here is actually the contact resistance, and also on this side, the contact resistance. And then I will show you also in measurements, which are quite precise that we did. And I will show you how contact resistance is actually also seen. And then in the middle, only here in the middle part with green, shown in green dashed lines, this is ion-electron interaction generally. So this could be like in NMC where we had a reaction, so charge transfer resistance, and also we had an insertion, traveling of ions, and so on. Everything is hidden in this element. So this can be worked out so that it fits the particular model that you are having. And here in lithium, you don't have that. Of course, you don't have any insertion. You just have surface reaction. That's all that you have, for example. So you have to adjust your model to the particular case that you have. So yeah, okay. So this is basically the whole cell model. And now I will go to analysis and also some experimental results. So now this is insertion cathode, let's say NMC. Now the elements are split, are made, they're not general anymore, but they are particular. So here is double layer capacitance, here is charge transfer resistance, Warburg impedance for diffusion in particles, NMC particles. And then here we have migration of one type of ions, the other type of ions. Here we have some double layers at the aluminum slurry contact, and here are chemical capacitances. So that's it. I mean, it looks rather simple, but if you plot this, if you generate out of this scheme here that we have some general impedance spectrum, this is what you get below. So as you see, this is even much more complex than shown before by Abbas. So there are many more features, or specifically there are 6 features. So several quasi-arcs or arcs, some electrolyte resistance here, diffusion, and so on. Of course, in reality, you don't see this. Because why? Because some processes are actually coupled, because they have different similar relaxation times, they are coupled. So instead of 3 features, for example, you will only see 1. And this is what was already shown before. But I will show you how this can be actually also, in some cases, it can be decoupled. So even if you have quite, let's say, coupled system with small amount of features, you can experimentally make some approaches where you can decouple at least some of the features. So here is this contact resistance, as you see here, it's a combination of these and these here. Now, the nice part, or the nice, let's say, part of this kind of modeling is that each of these sections here, which represents different processes, can be calculated analytically. So here are the equations. So for example, this section C here is given by this equation, analytical equation, and this equation only contains elements that are here. Or this equation for E, or section E, diffusion in separator, contains elements that are also here. So you can calculate actually for each process the resistance for this process. So this is maybe an added value for this kind of approach. It's very easy. I mean, easy. It's very straightforward. It's not so easy. You have to it takes some time to do that, but then once you do that, it's really very straightforward. So now I will show you examples. Measurements. I have our own measurements, which are done in our lab. So here is, for example, measurement for 1 molar electrolyte, and here are our simulations using that circuit that I showed you before. And now, if we look at this spectrum here, you will see many fewer features than shown before in the expanded, in the decoupled section. If you analyze this, you will see that 3 features are here coupled. And now the question is, can I make some decoupling of this feature in experimental way? And the answer is yes. For example, I decrease concentration. So I go from 1 molar to 0.1 and 0.1 molar electrolyte. And you will see that here some feature is appearing here and is really appearing to the full extent here. So beside this, you have an additional arc here. And what is this arc? In terms of my notation before, this arc is still not full resolution, but now instead of having 3 features, we have here 2 features coupled only, and feature F, which is actually the diffusion in solid particles, is here. So at the end, so very small amount of this F here, but you can see this clearly from the simulations. Now there are some. So you can see that basically all the features, also this 45-degree here or 45-degree here and so on, that you see in the measurements, you also see here in the simulation. But here, one feature probably is missing, and you see here a slopy curve, and here is always 90 degrees. And here it is, I mean, in theory, it's 45 degrees, and here is more. So now the question is, why is this less than 90 degrees? And why? I don't know exactly, but I can tell you possibilities. So one obvious reason is, the possible reason is that what we have in reality is different particles. Different particle size will generate some inhomogeneity, and of course we do have different particle size, only that we don't know the distribution. So, but we can guess. So, and let's say that we have normal distribution like this here. Let's pick 3 normal distributions with different widths. And then we plot the graphs, and we see that this 90-degree here transforms into this kind of what we really observe in our measurements, actually. Now I want to say something very clearly. Okay, with a certain kind of distribution, I can fit the measurement to any degree of, as you like. But why don't I do that? I don't do that because I don't know our distribution. If I knew our distribution, I would plot here instead of imagined distribution here, the real distribution, and then calculate and then see if fits to the measurements or not. So this is something that we practice. We try to practice. Until now, we don't have this particle size distribution. So I'm not showing this because we don't have it. We still don't have it. Maybe we will have it sometime. In any case, doing such kind of analysis, you end up with certain results. And of course, some results are shown here. So what we have, we can, for each section or resistive section that we have, we can get a value and then compare, okay, at 1 molar case, the biggest contribution to resistance is due to charge transfer resistance, and the others are less. And then if you change concentration, this will change. Now, of course, this may be very interesting for practice, because if you see that your charge transfer resistance is big, you try to decrease particle size, whatever, something that you decrease this and you have lesser or smaller total value. Of course, out of that, because this is physics-based approach, you can calculate any kind of physics parameters that appear in PNP or Newman's model, like this. So here is chemical diffusion coefficient, transport number, conductivity of electrolyte and separator, and chemical diffusion coefficient in the NMC. These are 4 examples, for example. Then you can repeat the story with lithium. you can see, I mean, someone who has done some simulation of lithium battery, lithium metal, will see soon that this is really very extended semicircles, and I will show you later on very briefly that these corresponds to porous dendritic lithium. But for our present purposes, I will just skip this and say, okay, we have a model, we have some input, and then we can actually, this was one of the questions before, we can predict what will happen with the whole cell. So we have half cell of symmetric cell of NMC, and symmetric cell of lithium, and now you can take half of each and sum up and see what happens. And here is the measurement of full cell, and here is calculation from symmetrical cell. So what you can see is actually that all these features actually are the same as predicted. I mean, as here as measured, and also in the calculation. Only the size of features is a bit different. This feature is a bit more bigger. This is also a bit bigger, but even the frequencies are matched quite well. Not exactly, but quite well. So it works somehow. I mean, you can predict from symmetric cells the full cell response. And of course, with some polishing of your model, you can actually fit the full cell to every detail as necessary. Okay, now so this was only introduction, of course. Now you have to use this somehow in certain way. And here is discharge curve for a typical lithium NMC cell. And at points that are designated, impedance spectra were measured. So here are the measurements. And now the question is whether we can use the model that I showed you just before to explain something about those variations. So impedance varies through charge-discharge quite a lot. I mean, there are different kinds of varying features. So the question is, can we tell what is going on during charge and discharge? And the answer is, yeah, we can. Here is measurements, and here is simulations. Now, I will tell you how we came from the measurements to the simulation. We observed a lot of these measurements, and we saw that you can basically cover all the changes during charge and discharge by only varying 2 parameters. Out of many parameters that you have in cathode, anode, and separator, you only vary 2 parameters. So you relax 2 parameters, all the other remain the same, and you fix them. And then you can describe very accurately, as you see. I mean, I think this is very, very good description. Very accurately what is going on. And which are those? One is chemical capacity. This is actually the capacity of storage in NMC. This is chemical capacity, one of the elements that we have in our cathode. And chemical capacity can also be calculated from the slope of the curve. Inverse slope of the curve is actually chemical capacity of the charge-discharge curve. So you have the slope, you have curve, you have its slope, and inverse slope at each point it is different. And you can compare that calculation with this, where you have impedance, and you see that the trend is completely the same, except that impedance is always lower. And why? And the answer is quite straightforward, because we didn't take into account distribution of particle size. If we took, I mean, we could calculate this. If we took appropriate distribution of reaction size, we can fit this curve, this charge-discharge curves with impedance data from chemical capacitance, almost, I mean, to several percent of accuracy. Error. So the other parameter that is changing is the charge transfer resistance. And charge transfer resistance is actually incorporation resistance of simultaneous of electron and ion into NMC particles. This is changing. this is known, it has to change, and the theory, I mean, the general theory, which is not valid completely for batteries, we have better theories in the literature, but theory gives the same shape or a similar shape, this bell shape, and you can see that impedance will tell you also there is a bell shape. It is not symmetric. That's interesting. We still are working on explanation of that, but you can extract this kind of data. So only these two changes, and you have all the fitted curves during charge and discharge. So now I will very briefly, in 5 minutes, maybe go through the rest of the talk. I have maybe 5 to 10 slides more, and I will just say that, like as I announced before, like we are using this in NMC insertion materials, we can also go to non-insertion materials like surface reactions and so on. So here is the generalized reaction, which can be surface, volume, or whatever. And this has been used a lot in our lab, as I said before, maybe on lithium or on polysulfides in carbon and so on and so on. So sulfur batteries. So here, before I go on, I would just like to mention that for this kind of situation, there is in the literature there is an analytical solution of the Newman's model, and we can compare our predictions of our model with the Newman's model with this analytical solution, and this is our transmission line, so red and blue, and you can see that you can make some correlations here, like here briefly shown, and you can see that it's the same. So there is no difference in physics of the Newman model and this PNP actually model that we're using here for making this transmission line. You get, for different conditions, you get different spectra, but there is a very good correlation between them. Now, also validation of this approach, for example, for sulfur electrode. So here we used felt, carbon felt. We poured in electrolyte, and there is a surface reaction of polysulfides on this on the surface of these fibers here. And then what you get when you put also, of course, symmetric case, one and the other electrode, and in between a separator, you get something like this. Here are the measurements on the left, and on the right, there are reproduced, I mean, very well reproduced shapes and sizes for this transmission line model. Also for conventional carbon, so this was, before this was a model carbon, this is a conventional. The porosity was changed, the features change a bit, but you can predict what will change in your spectra, in your model, and you see that this prediction fits very well to what you observe in reality. And now, the same as before, you can calculate all kind of, you can get out of this model any kind of physical parameters here. And now also lithium, you charge, discharge symmetric lithium cells, for example. You see very big change in the shape. So here you have semicircle, it gets smaller, it gets distorted. Here you have some feature, small feature, it grows. It is elongated a lot, and this seems hopeless if you look at this, how to model this. But if you look into the literature, you will see that in the beginning you have lithium, of course, bulk lithium. On top of it, you have SEI. Here you have separator. Then during cycling, you develop porosity, and you have two kinds of porosities. One is porous lithium, like metallic live lithium, still connected to the bulk. And then some lithium actually just dies out because it reacts totally, and it is called dead lithium. It's not lithium anymore, it's a salt. It's called dead lithium. And you can observe this under a microscope. And then if you take into account these morphology changes, you can, and you'll see these morphology changes throughout cycling, you can create this kind of model. It's an upgrade of previous model. So we have this dead lithium more here. You get this kind of shape, general shape that we observe out of this, and of course you can make analysis. just as I said before, the good part here is that we have a lot of morphological data, so we could take into account this morphological data, put it into the model, and then we could, well, all these cases, and it was about 50 or 60 such figures that we made. We got some correlation between what you measure and what you actually can model, and then we tried to understand what is going on. Then we predict the different scenarios. Some are the same as already existing in the literature, some are a bit different. And then we also said, okay, this scenario corresponds to this kind of modification of shape, this to this, this to this, this, this. So you can get some, let's say, some, yeah, some table. You have different scenarios, and based on impedance that you measure, you can identify these scenarios. And just the last slide. So we are also dealing with magnesium batteries a lot. Why do I mention this? Because up to now, and also before in the previous talk, if you remember, the biggest impedance contributions to the battery cell is from transport. So you have transport, and reaction also gives some response, but it is small. I mean, rather smaller than the transport itself. So now in magnesium batteries, it appears that once you activate a magnesium battery, most of your response, or let's say more than 90% of your response, pertains to the reaction at the surface. How do we see this? So when you activate magnesium, you crack down your passive film that you always have on your magnesium, and you have a crack, and here you have some fresh metal. And now on this metal, well, there are some reactions that depend on what you have in your electrolyte. And then this gets quite complex. For example, there is one possibility. You can assume that this magnesium will transfer into ions. So somehow this will absorb on the surface, like these yellow particles here. Then they will maybe dissolve, or maybe they will transform, because you have chloride here, into chloride species, and then these chloride species will dissolve and so on. So you can create a certain kinetic reaction, which can be complicated. And from experience that we have from previous work on corrosion, we know that if you see this kind of spectra here with these loops here, then you would have some absorption like here. And we figured out a model out of this. So you can calculate this analytically, actually. These kinetic, there are just several kinetic equations together, and you can calculate them. And even, I mean, a rough analysis shows you all these kind of shapes. It's interesting that from here to here, so these are different cycles of magnesium. Magnesium, it is symmetric. You see some drastic changes in shape, but if you analyze this, you will see that this just means that there is a little bit more and more of this, and a little bit less and less in this as a cycle. There are no other essential changes, and you already get this spectra, which fit quite well to the measurements. So in continuation, I think the community will also have to focus on this kind of reactions, because magnesium, aluminum, and other newer types of batteries, they contain a lot of surface chemistry, surface electrochemistry, and maybe this is slow. Because this is slow, the transport becomes relatively fast, so you have to focus on this interface. So thank you very much, and I also want to thank many people, and also some financing.
Thank you very much, Miran, for this fantastic, amazing talk. Thank you very much.
Thank you.
You have many questions waiting for you in the question session. I may ask maybe a small question before. So in your slide 12, when you show the impedance spectra for symmetric cell conditions, so are you using a blocking electrolyte or not? So maybe I missed that point.
Electrolyte? No. Why do you think it should be? I mean,
no, actually, I'm saying that because what Abos showed before is with a blocking electrolyte, so there is no insertion in MNC.
Oh, no.
And then the shape will be different,
No.
right? Yeah.
No, of course.
Yeah.
Now here we have lithium, of course.
Okay. Good. Okay, so you can maybe go to the question session. You pick a question and you click in the Start Live Answer, and then.
How do I do that? Sorry, I don't know. Questions. Oh, okay.
Okay. Yes.
I press this. Yeah. Okay.
You press the Start Live Answer, and then you answer a question. So you should press. Yeah. Great.
Okay.
Yes.
What is the advantage of your transmission line over obtaining impedance directly from the human model? I think it's more visual. I mean, there is no real. It's more visual, and you can relatively easily develop certain analytical expressions, as I showed. So that's more or less. Okay.
Miran, there is a question from Emiliano in the chat. Maybe you can move to the chat section.
Sorry, yeah. From who?
From Emiliano at the bottom of the chat.
The bottom. Oh my God. It's moving very slowly. Yeah. Who? There is.
There is Emiliano Primo in the very, very bottom. Also, there is a lot of questions waiting for you in the question session. I mean, you can continue with the question session.
I'm looking at the question. No, I'm looking at the question session now. So
yes. Go ahead with question session. Yes. Fine.
Okay. Sorry. So I don't know how to pick the questions because there are so many. I mean, everybody who has a question can write me an email whenever I will answer. I have some problem with connection. Yeah, I don't know. Now it's back. I had some problem with connection. Yeah.
I can, if you want, I can pick a question for you and then you answer the question.
Please.
Okay.
Please do it. Yeah, it will be faster. I have some transmission problem.
Okay.
Transmission line.
Yeah. So.
Yeah.
Yes, you can read the question, right, in the screen?
Yeah, it's it's a similar question as before.
Yes.
So it's there is no advantage. Maybe it's I mean, for me at least, who I'm doing this a lot of time for a long time, it's even easier to construct some, let's say, some new versions of models, because in Newman you have to, of course, calculate everything from the beginning somehow. And here you just use these transmission line elements like Lego sort of way. But you have to be sort of experienced. Otherwise, you will make an error.
Good. So I pick another one. It's random, guys. Sorry, I'm picking randomly.
Yeah. Of course. How to differentiate the electrode blocking phenomena with particle size impact in low frequency region? If you have electrode blocking phenomena, this would lead to supercap. I mean, something like that probably, because you will only have double layer on your particles or walls or whatever you have, and then you can change the specific surface area of your particles or walls, whatever you have. You can change electrolyte concentration as well. You can change the thickness of electrodes, and these are bits to do, but I think combined you will get some insight into that. So
okay.
So maybe I forgot to say, but it's very important. I mean, the important part here is not the modeling itself. I think modeling is very important, but as we saw also before, even more important is to make a lot of so-called, let's say, experiments, dedicated experiments, where you vary in a controlled way various parameters like electrode thickness, separator number or thickness, electrolyte concentration, which I already showed, temperature, if you can. Many things you can change, and then, or you change electrolyte type also, and then it has. I mean, the model, if it is okay, it has to work for all these kind of variations. Otherwise, something is wrong with the model. Something is missing or something is wrong.
Yeah.
Yeah. So in slide 11, could you give more insight on the semicircle C? Yeah, semicircle C is actually due to a sort of combination of transport and reaction inside your pore. It's I didn't put a formula, explicit formula. It's complicated, but you can get this size of this simply by taking D minus. You have this C. This is something that people don't realize. It exists always there. It's also in the Newman model. So this C prime is really very important, and it can be shown. I mean, I can answer you with in more detail in email if you wish.
Okay. Yes. This one.
So, but max was significantly higher in previous slides. Why did you limit the frequency for a full? We didn't limit the frequency. Maybe something was missing, but shouldn't. I mean, we didn't limit. The frequency was always, the top frequency was always on the range of 100,000 or something like that. So we didn't limit. There could be a mistake. I don't know right now. But there was no limitation. It was the same. I mean, what we did actually. Which type of cell will symmetric cell is really very good. As I showed you, you can see, but you have to construct it yourself somehow, because if you're using some more commercial, then you cannot really control the thickness or whatever is important to control. But symmetric cell is a good start to study one electrode, because everything is just multiplied by 2. Symmetric cell and you put some separator, maybe vary the type of separator, the size of separator, and so on, and also the thickness of electrode slurry, and then you are already quite progressing. And then later on, you go to the full cell. That's my opinion.
So let's pick a last question. Can we go to email so we can forward? Yes, okay. There is someone who is asking for your email. So maybe you can write your email in the chat.
Yeah, sure.
You have on the left of the question, you have the chat, and then you can write your email.
It works, yeah.
And people can contact you there. You can also, I invite you to answer in the question session. You can write also your answers. Probably it's easier that maybe you will receive 20 emails. Maybe it's easier you write directly when people ask a question, so you write directly there.
But I don't mind if I get a lot of this kind of emails.
Good.